Before we get into lots of more complicated Taylor series stuff, let's step back and see the big picture here. So let's say a big idea of Calc 1 is that if you zoom in enough, most functions look linear. That's where we got the tangent line idea from. That's where we talked about the derivative for very, very small time steps, the time step approaching 0 in, up to infinitesimal sizes. So then what's the related big idea of Calc 2? It's no longer that most functions look linear, it's that now we're approximating with other functions, right? And those are important because we've kind of zoomed out a bit from being zoomed in so far everything will look linear. So we could say if you zoom out a bit from there, then functions tend to look quadratic, right? Or parabolic, maybe is a better word. So we're saying P2 of x equals f of c plus f prime of c times x minus c. That was our tangent line formula, plus now f double prime of c times 1/2, or 1 over 2 factorial, x minus c squared. So there's our parabolic term. And then, if you zoom out a bit from there, what tends to happen? Then P3 of C is an even better approximation. So it's, let's just say it's P2 of C plus f triple prime at C times 1 over 3 factorial x minus c cubed. So things tend to look cubic then. So let's go see that in Desmos. So here I've got e to the x in red, and I've got the tangent line 1 plus x in blue, and those look pretty close. The function looks pretty linear. But then if I start zooming out, we can start seeing some curvature, which looks kind of parabolic, and so then I can start my parabolic approximation. That's looking pretty good. But over here it's not doing so well, so it's not looking exactly parabolic. So then I would turn on the graph of my cubic approximation. That's looking even better. And so when I said if you zoom out more and then I wrote the P3 thing, I didn't mean that only works if you zoom out more. It's just it feels more necessary because we start seeing the curvature more. Another way to say it, in Calc 1 we did a tangent line, and another word for that was what? It's a linearization of the function. It's saying, hey, let's treat the function as if it was linear. So we could say it's a linearization. In Calc 2, our Taylor polynomials is, well, they aren't linear usually, so you could say they're a polynomialization, but it's a generalization of this idea. That might, anytime you see the numbers 1 and 2, that makes you wonder about, how about 3, right? So what do we do in Calc 3? Well, we do Taylor polynomials, and sometimes they're linearizations, sometimes they're polynomializations. Depending on what order you want to do things in. But it's a linearization in multiple dimensions, so it's actually planes rather than straight lines. So planes and hyperplanes approximating functions. And if you start curving things in 3D, you get kind of ellipsoid surfaces, which is a 3D version of parabolas and hyperbolas and ellipses and stuff. So that's kind of where this is all going, and that's really useful when you're doing optimization with more than one variable, you can say, I'm going to approximate my function with this ellipse or ellipsoid, and then the minimum is at the center of the ellipsoid, which is easy to find, and then you go there and do a new approximation and stuff. It's called Newton's method, and we'll talk about it later. Let's do another quick thing. Nobody really likes writing out x minus c repeatedly, right? So let's talk about avoiding that. So let's say we've got our anchor point C here, and some value x some distance away from it. That's what we're usually thinking. Let's think about this distance. You might call it delta x, how much x changed from where you were anchored to the new point. In Calc 1, we often called that h. We could call it x minus c. You could also say that x equals c plus h, right? Start where you were and then move a small distance. That's a good way of thinking of it. So instead of writing p of x equals f of c plus f prime of c times x minus c plus f double prime of c times 1 over 2 factorial x minus c squared, etc. Anywhere you see an x minus c here, you can replace it with delta x or h. H is even shorter to write. So we could write instead p of, and then anywhere you see an x, you could replace it with c plus h. So you could say our polynomial at c plus h is f of c plus f prime of c times, and instead of parenthesis x minus c close parenthesis, you can just write h. And then here you can write f double prime of c times 1 over 2 factorial. And instead of parenthesis x minus c close parenthesis squared, you can just write h squared, etc. This is what's called the incremental form of a Taylor series. And in its simplicity, it kind of makes us think of a Maclaurin series, right? Or Maclaurin polynomial, because for Maclaurin, we didn't keep writing x minus c in parentheses and square it and stuff. We just had x, x squared, etc. So this is basically a Maclaurin way of thinking, but centered at c instead of centered at 0. So it's a way of writing stuff in a little bit more convenient of a notation.